So that being said, when we do a related rate, okay, we're talking about derivatives. So if I wrote this, dy dx, just standard derivative notation. This is our derivative of y with respect to x. You okay with that? The rate of y with respect to x. This is the rate of y with respect to t. This is the rate of v with respect to t. Doesn't matter what the letters are. Are you okay with that? Okay. So I'm going to give you a similar problem that we saw last time. Let's go with x squared plus y squared equals 25. So we saw this. Notes, saw it homework. Circle problem here. And this is the way I'm going to write it. Find dx dt. So not dy dx. I'm finding dx dt where dy dt equals 2 and x equals 4. Now, as soon as we see these two guys right here, this is telling us a derivative. This is telling us a rate. I'm looking for the rate of x with respect to t. I'm given the rate of y with respect to t, being 2 units. But 2 rates. We call this a related rate because we're comparing more than one rate. Now I'm going to look at the derivative. The only way I can compare the rates is if I actually get the rates. I need that derivative. So before you were asked to find dy dx. I don't want dy dx. I want dx dt, dy dt. I want derivatives with respect to t. X squared. What's the derivative of x squared? Okay, so we're going to have 2x times the derivative of the inside, dx dt. So last time it was dx dx because we were finding the derivative with respect to x. And I know that canceled, but remember how we actually wrote it to start with and go, remember this is what's really here. Now I'm finding the derivative with respect to t, so I have dx dt. Plus, everybody agree 2y for the y squared? Dy dt equals 0. It's still a constant over there. It wouldn't matter if you put a dt underneath, it's still 0 times it. Are you okay there? All right, now we're looking for dx dt. So I know 2. I know 4. I don't know dx dt, which that's okay. That's what I'm looking for. Plus 2. I don't know y, but I know dy dt, that's 2. 0. This is a very simple problem if I know what y is. Fill that in, I can solve for the dx dt. Not a big deal. And we have enough to get y. Because it says x is 4. So if x is 4, that's going to make y 3. Everybody agree? So that'd be 16, 9, 3. Now I can finish out the problem. So that means that dx dt, what would that be? 6, 12, divided by negative 12 eighths or negative 3 halves. Does that look right? It would be that rate.
Where are you getting the negative from?
Subtract this over.
Okay.
So I'm trying to get this guy along. Now that does not mean that dx dt is always negative 3 halves. It's negative 3 halves at the moment the rate of the y is 2 and the x value is 4. If those rates change, the dxt rate changes. That's why we have related rates. You've got two things going on at once. Now, another way of thinking of related rates are application problems. We're going to look at a few application problems here today, and this is where I'll just give you a handout so you don't have to copy the sentences off the board. Okay. Think of something like this. All right. If you were put the stopper in and fill a bathtub, think of the rates that are happening. You have the rate of the water coming in. You have the rate of the height of the water changing as it's filling up. Which means you also have the rate of the volume changing. That makes sense to everyone? Pull the plug, you've got a fourth rate leaving. And if the rate leaving is not as fast or faster than the rate coming in, it overflows, right? You have more coming in than you have going out. That's a related rate. In other words, when one rate's happening, everything else is affected by it. All the other different rates get affected by it. You blow up a balloon. Air going in. There's a rate. What's happening to the balloon? It's getting bigger. If it's a circular balloon, the radius is getting bigger, right? The radius is changing. The volume's changing. You let air out, it's coming back down. It's still changing. All right, it's still a rate that's changing. Those are related rates that we're going to be working with. Okay. So let's look at some of these other problems, and we're going to compare the different rates here for our pieces. All right, so we have everybody's favorite word problems today, right? Application problems. When we're working with these application problems, we got to figure out what we're dealing with. Do we need a picture? Do we need a formula? What have you? Okay. So on the first one, spherical balloon being filled with gas such that when the radius is 2 feet, radius is increasing. No, wait, radius is increasing. It's getting bigger, right? Radius is increasing at 1/6 foot. How fast is the volume changing at this time? Volume of a sphere is what we're working with. We don't really need a picture. We have a formula for a volume of a sphere. Now at this point, or anything, I wouldn't worry about memorizing anything about the different old geometric formulas. Volume of a sphere was 4/3 pi r cubed. I will give you formulas. They're in your book. You can look them up. But right now, we just want to be able to work with it. Okay. Now let's think about some rates here. If we're talking about a rate change, it refers to the derivative. When I look at that equation, how many variables are there? Including v. Maybe 2, yes. We have the v and the r, right? So that means if I do the derivative, I'm going to have 2 variables that are going to have differentials. They're going to have rates. I'm going to have a dv and a dr. Everybody agree? And this will be a dv dt and a dr dt with respect to time, because look at what they gave you. In the problem it says the radius is 2. So I'm just going to write out here to the side, radius is 2, and then it says dr dt is 1/6. It says the radius is increasing. Words like increasing, decreasing, those are referring to a rate. It's changing. Okay? So it's increasing at 1/6 feet per minute, right? Well, there's your time. So we know that this is, radius is 2 feet, and this is feet per minute. So that's how I know when I said dv dt, dr dt, I knew it was with respect to time. We're asked to find out how fast the volume's changing. That would be the variable dv dt. That's what I want to know. So if I need a picture, I'll get a picture. If I have a formula, I'll get a formula. I'm going to write down what I'm given, what I know. I'm going to write down what I need to find. Okay. Now I'm going to look back at my problem. Let's get that derivative. We need the differential because we're looking for a derivative here, and we have this differential. The derivative of v, dv, dt. Technically, it would be 1 dv dt. You okay with that? Right side, power rule. 4/3 pi is just a constant. I'm not worried about that. That 3 is coming down. So if that 3 comes down, 3 times 4/3 is just 4. Pi r squared times the derivative of the inside, dr dt. There's that chain rule. Now we're going to substitute in the values we have and see if we need something else. So in the last problem I had on the board, we substituted in, we still needed y, we went back and found y. Okay? Well, now let's substitute in, see if we need anything else. If we need it, we can go get it. I'm looking for dv dt, so I don't mind that being blank, or not knowing. 4 pi, r is 2 at this moment, squared. Dr dt I'm given is 1/6. Are you okay with that? Now, I don't care if fraction or decimal or anything, but here you'd have dv dt. Oh, what's that going to be? 4, 16, 6, 8/3 pi. I don't know what the decimal is. I don't have my calculator up here, but I don't care if it's a fraction or decimal. It's not going to make a difference. Now my units. Volume. Is volume singular, squared, or cubed? Cubed. That's how I remember. So we're going to have cubic feet, so feet cubed per minute. That was my time element in this problem. So I did not have to go back and find anything else. I had all the pieces that I needed. So I'm going to start with picture if it helps. In this case, I had a known formula. I went right for that. I'm going to write down what I'm given from the problem, write down what I'm looking for. And then I can look at those differentials and decide, do I need something more? Do I have everything I need? And in this case, I had everything I needed. Solve it out. Look at your derivatives. No new rules. Derivative of y is 1. Derivative of x is 1. Derivative of v, 1. It's just a variable, right? Chain rule. We're doing with respect to time, so 1 dv dt. Right side, power rule. I know it looks different sometimes with that 4/3 pi sitting there, but that's a number. So 3 comes down. Cancels with the third, and I'm left with 4 pi r squared times the derivative of this inside, which is dr dt. Everyone okay there? We're getting some different looks now for sure, but no new derivative rules. Different looks. Let's look at the second one. All right. Person 6 feet tall is walking away from a street light 20 feet tall or 20 feet high at a rate of 7 feet per second. What's the length of the person's shadow? This one I probably need a picture for. It's not some known formula like a cylinder or sphere or something like that. So I'm going to create a picture here. What I have is a person walking away, and this is going to create a triangle. So I've got this 20, and then over here I've got this 6. Now I don't care if it's really to scale or not. That doesn't matter to me. I'm just trying to get that general shape. Okay? So I've got a 20-foot tall pole. Person 6 foot walking away. So obviously, if I'm walking away from that tall pole, well, the further I get away, the angle is going to be created from the top of the pole over my head. Something like that. Everybody okay with that? All right. Now, what we're also given, he's walking away, the person's walking away at 7 feet per second. 7 feet per second. At what rate is the person's shadow increasing? All right, I need some variables up here. On the bottom here, I'm just going to put an X here and a Y here. Or, and maybe this will help us out. Let's do it this way. So we'll call this the shadow so you can keep it with the wording of the problem. There's my shadow. Shadow's in front of you, right? If you're walking away from the light. Does that make sense to everyone? Okay. And what do you want to call this over here?
Travel.
Travel. Again, we can put letters in there. We're just trying to get something for you to recognize. It does not matter. It's just a variable to us. Okay? Everybody okay with that setup? All right, now what I'm given. Okay? Person's walking away at a rate of 7 feet per second. So, is that the differential of the traveled or the differential of the shadow? Traveled. All right. So, D traveled, dt is 7. I'm looking for the length of the shadow, so that would be d shadow. dt is what I'm looking for. And again, I put words in here instead of variables to make you understand it really doesn't matter. We're talking about different rates. Okay? Typically, I know I wouldn't use an S for a variable because it looks like a 5 half the time when I write it. All right? But I don't care if there's a word in there or not. It's not going to change anything to me. Now we've got to come up with an equation that's going to compare this. Now this would go back to quite a while back for you. This would be a similar triangle. Notice how they're both right angles. We weren't giving any kind of lean on the pole. We're assuming the pole's vertical. And we're assuming the guy's not drunk. It's vertical. Walking through there. Okay. So, right angle, right angle. Now look at the small triangle and the big one. They share this angle, right? So that would mean these two angles are the same. That's how we get that similar triangle idea. So this small triangle is similar to the big one. So again, these two angles are the same. They share this one, so that's the same. And since all triangles add up to 180, those two have to be the same. It's creating that similar triangle. Well, this will be a case where I do kind of need a picture to see that. First problem, I had a formula. Not a big deal. I kind of needed that picture here. So we're always going to need a known formula or some kind of picture to help us, or maybe both sometimes. So now let's set up our similar triangle piece. Traveled plus shadow over 20. There's my first ratio. Equals shadow over 6. Now there is multiple ways we can set up a proportion with similar triangles. So basically what I've done is I've said the base of the big one over the height of the big one is proportional to the base of the little one over the height of the little one. And so when you're setting up proportions, what you should remember is you've got to keep in line, hey, what's on the top left is on the top right, bottom left's bottom right. So I've got the base on the top left and base on the top right, height top left, height top right. You can flip both. You just got to make sure you're staying consistent. Does that look pretty familiar? And again, I know it's been a while since you looked at some similar triangles. We're talking about familiarity here, not perfection. It should look like something you've done before. Okay, well, let's kind of finish out the equation here. I need to kind of get some stuff alone here. So remember how you could cross multiply in your proportions? To kind of clear out these fractions. So I'd have 6 traveled plus 6 shadow equals 20 shadow. Now I've got like terms on both sides. I can subtract that 6 over. So I've got 6 travel equals 14 shadow. Everybody okay there? We can even put the numbers together. Let's see. I can bring the 14 over. And that would be, what would that be? 3/7 travel equals shadow. Again, I'm just sticking with the words because that's what I started with. I don't care what's in there. But a lot of times if we're going to create an equation, if we can solve for one of the variables, that makes the differential easier. We can even see that back in the form, and then we haven't solved for b. That made this differential a little bit easier on one side. We can solve it. And it wouldn't have mattered in this case whether I got traveled alone or shadowed alone. The only reason I made it where shadow was alone, I'm looking for D shadow. It wouldn't have mattered if I got traveled alone. I could still solve for D shadow. Everybody okay with that? Okay, now let's look at the differential here. 3/7, not 3D. 3/7. D traveled over dt equals D shadow over dt. So that travel is just a single variable, just a t. I didn't have t squared or anything like that. Now I know the d traveled 7. 3/7 times 7 is my d shadow. dt, hey, 7 cancels, so the shadow's changing at 3, and we were in feet per second. Shadow's changing at 3 feet per second. Okay there? Okay, skip down to number 4. We'll come back to 3. Read number 4 to yourself. Think about what kind of shape we have and what's going on. Okay, what kind of shape do we have? Triangle. So you get the ladder leaning up against, it's going to create a triangle, right? Triangles aren't too bad. Some of you would be fine without a picture. Others need a picture. The picture helps me because to me, triangles have a lot of formulas. Triangles have all the SOHCAHTOA stuff, Pythagorean theorem, things like that. All right, so sometimes a picture does help me for a triangle. Here goes my triangle. The ladder is leaning against the wall, so this is 5. That's the ladder. Now, I didn't put a variable on the ladder part. Any idea why? It's constant. The ladder's not changing. It's a 5-meter ladder no matter what. All right, the ladder, I don't care how high or low you put it on the wall, it's still going to be 5 meters long. It's just changing the angle. So it's a constant piece. All right, start sliding down the wall such that it's moving away. How fast is the top of the ladder descending? At the instant the foot of the ladder is 4 meters from the wall. I need some variables here to see what's going on. Okay? I'm going to go X there, Y there. Why am I using X and Y? I feel like it. There's no other reason. I'm just picking two letters. Okay. You can put height, away, do whatever you want. Okay, they're just variables. So how fast is the top of the ladder descending? So that means this is coming down, right? So I'm looking for dy dt. How fast descending? That's referring to a rate. Okay, so I'm looking for that dy dt. At the instant, the foot of the ladder is 4 meters. So x is 4. Now remember, this is changing because think about this as the top of the ladder is coming down, the bottom of the ladder is going out, right? So at the moment, this is 4. At that very moment, I'm told that the ladder is moving away at a rate of 2. So dx dt would be 2 meters per second. Everybody okay there? Okay, what known formula or relationship relates to 3 sides of a right triangle? Pythagorean theorem. All right, so now let's look at my triangle here. X squared plus y squared is 25. Everybody okay there? All right. Okay, now take the derivative of that. We need to look at the rates. We got to do the differential. Go through the differential there. Look up, check your differential. See if you agree with that. I haven't solved anything, but I found the derivative. Everybody agree with that derivative? Okay. Now let's get the pieces in there. 2. X is 4. Dx dt is 2. 2. I don't know why. I don't know dy dt, but that's okay because that's what I'm looking for. So I've got one blank I've got to fill in. Everyone okay there? What would that y value be that I'm going to fill in? 3? 3?
Yes.
Okay. 3, 4, 5. Everybody okay with where we're getting 3?
Yep.
Put 4 back into that Pythagorean theorem. Solve that, I've got 3. Now I'm good to solve, right? So dy dt would equal, let's see, 8, that's 16, negative 16 over 6, or negative 8/3 meters per second. Again, I don't care if you use a fraction or a decimal, it doesn't matter to me. Everybody agree with that? Why is it negative? It's descending, it's going down, right? The height's going down. So there's actually a couple ways you could answer this question. Right? You could say that it's moving at negative 8/3 meters per second. You could say that it's descending at 8/3 meters per second. You wouldn't say descending at negative 8/3 because then that would actually ascend. You'd have a double negative. So you have a couple ways of answering that, but we need to understand that negative just means it's going either backwards or down or something like that. Pretty good there? All right. Now let's look back at number 3. All right, there's my formula for a cone. 1/3 pi r squared h. And again, like I said before, I don't expect you to remember that. That's okay. Okay. The way we get the formula for a cone, it's actually 1/3 of a cylinder. The cylinder was pi r squared h. There's that piece. All right, so I've got how many variables up there? 3. V, R, and H, right?
Yes.
Okay. That means I'm going to have 3 differentials. Everybody okay with that? All right, now before I find the derivative, let's take a look at what I'm given, what I need to find. All right, so on here, they tell me it's 20 foot high with a circular base whose radius is 5. So for some of you, I know myself included, sometimes a picture helps. There's my cone. 20 feet high with a radius of 5. Water's running out of the bottom of the tank at a constant rate of 3 cubic feet per minute. Water running out. That's a rate. Is that dV, dr, or dH? dV. So dV dt. All right, now what's the other clue other than just the wording that this is the volume rate? Cubic feet. There's that clue. Right. So I've got the water running out at 3, so dV dt is -3. Why negative? Running out, so the volume's going down. Okay, volume's going down. How fast is the water level falling? That's still a rate, so would that be the dr or the dH? dH. Water level falling, so that's dH dt. There's my question mark. When the water's 8 feet deep, and that's H, 8 feet deep. All right. Now let's think back to this. When you're solving an equation, you're trying to solve for a specific variable. Whether you're solving for X, for Y, for A, for P, it doesn't matter what the variable is, but you're solving for the variable. That means everything else has got to be taken care of, right? I want just that variable. So I've got a big problem here. I don't mind solving for dH dt, but I need to have dV dt, and I need to have dr dt. I don't have dr dt. That means that's an extra variable in my way I can't solve for. If I don't have dr dt, then I can't have r. Because if an r is in the problem, it's going to create a dr dt. Just like if there's a v in the problem, it's going to create a dv dt. Does that make sense to everyone? So this right here is what's telling me that I need to go through and get rid of r. No dr dt. It's all right up here. No dr dt. So need to eliminate r. Now when you're looking at that, remember, I know there was also no dH dt, but that's what I'm looking for. I'm not expecting to have that. I'm looking for that guy. So I need to eliminate r. And this is how we're going to eliminate r. You were given some information about the cone. Cones are uniform. They don't start here and then do this. They uniform, right? So as that height's changing, the radius is changing at the same rate. Does that make sense to everyone? Okay. So here's what I know. R over H is 5 over 20. There's my relationship between radius and height on that cone. Because when it's full, it's at a 5/20th ratio, and as it's moving down, it's going to stay in that same ratio. But Everybody agree with that?
So because they're going to stay at the same ratio, you're putting the R.
And it doesn't matter if you do H over R over H. This goes back to that similar triangle kind of thing. Whatever's on the top left better be on the top right. So if I put radius on top, I got radius on top. If I want to make it H over R, then that would be 20 over 5. Wouldn't change anything there. Everybody agree with that? All right. So that being said, here I need to solve for R. R would equal H over 4. 5/20 would be 1/4. I can move that H to the other side. There's my R value. So now I'm going to rewrite my formula. My volume's 1/3 pi H over 4 squared H. So I've substituted H over 4 for R. Now look at it. I have two variables. I'm going to simplify, but I still have two variables. I got an H and a V. I have two rates. One I'm given, one I'm looking for. I'm okay with that. All right. So let's clean this up a little bit. Let's see. This would be pi over. See, that's 16 times 3 is 48 H cubed.
Wait.
16. Oh, just is it? Oh, 16 times 4.
So why would the one? Sorry, I was writing slow.
I have H squared and H is H cubed.
So why would the H cubed not be in the numerator of the fraction?
Well, it can be. It's the same thing.
Oh, right. Ha ha.
Yeah, you could write it in the numerator like that. That's the same thing. Just depends on which way you like looking at it. It's the same thing, though. Okay, everybody good with what I have here?
Yes.
Okay, now we're ready to work the derivative. dv dt. Where's that 3 go? Front. So that'd be pi 16ths, because 3 over 48 would reduce to pi 1/16. H squared dh dt.
Wait, sorry, I was looking for a second. What? How? Sorry, what?
Power rule. 3 comes down. 3 over 48 is 1/16.
Okay.
You okay with that part? Okay, let's fill it in. See if we need anything else or we have everything we need. All right, we got dv dt is -3. Pi 16ths. H was 8. 8 squared 64. I can leave it 8 squared. And I'm looking for dh dt. I don't need anything else. I've got everything I need, right? Let's see. I can move the 16 over. So -48 over 64 pi is dh dt. That was reduced down to what? -3 over 4 pi. Reduce that. Oh man, somebody tell me what decimal that is. Get your calculator. Put the 4 pi in parentheses. .2387, so we'll go to 0.239. Round off. Okay. So we have net, and it'd be negative 0.239 feet per minute. Feet per minute were the units we're working with. Why is it negative? Other than the fact that the algebra gave me a negative, why would it be negative? Straight into the height's going down. Makes sense, right? Something like that. All right. Are you okay there?
Would it be cubic?
No, because it's the height. The volume's the cubic. This one's talking about the height. The height's changing just by feet per minute, not cubic feet per minute. Does that make sense there?
Yeah.
All right. Okay.